We are trying. Will you share your slide?
Yes, I will. Just a moment. Sorry.
No, it's completely okay.
So now you see my screen, am I right?
Your screen is showing, but no PPT is showing actually. Only a screen is showing that you are presenting.
So, shall I start now?
Yes, ma'am, sure.
Thank you very much. So, I would like to thank you for inviting me for this event. It's my great pleasure to meet your virtually. So, my name is Valentina Januk. I'm representing Hello Cooking in the University of Belgrade, Serbia. But also I'm representing the Interlock promotion, and most of the results that I will present today are coming from this project. So first, I would like to introduce my institute where I'm employed.
Ma'am, your screen is not visible. No. Ma'am, you should share entire screen mode. It is.
Is this now okay? Oh, sorry. Yes. So first I would like to introduce our institute, from Serbia. Then I will talk about the challenges that we have faced in the development of artificial intelligence decision support system. I would like to mention that this presentation is very much linked to practice. So it's at our institute is Applied Research Institute in Information Technologies. So we are developing projects, we are building new systems, we are building devices, and this research is part of that work. I will talk about the trustfulness evaluation framework that we are implementing or we are using in the Intellilarm project. So our research is Mikhail Pupin is funded by the Intellilarm project. So it's a project that is funded by the European Commission for the period from 2022 until 2027. So we are now in the middle of the project. I will talk about the results and some conclusions about these projects, how we are advancing, and what we will bring to the community with these applications. So Serbia is at a crossroad that connects Europe with the Middle East and Asia. So this is the red spot here on the map of Europe. More about research results of Institute Mikhail Pupin can be found on this link. The institute is leading Serbian research and development institute in ICT, the biggest and oldest in Southeast Europe, founded in 1946. And we are, as I mentioned, oriented towards the industry and businesses or the real problems. So, and the 90% of the turnover is by technology transfer. So, the applications or the products that we are developing are information systems, process control systems, traffic management systems, railway programs, defense program, and then other activities. So what we are very proud for in 2020, when the COVID was very actual, is that we developed the first Serbian respirator. So, and this presentation today is from healthcare. So we are talking about the trustfulness evaluation in healthcare. So we are talking about testing and validating of medical devices. So, but this, especially this medical device here is not certified yet. So the whole procedure for certification of such device is very complex and very expensive. So in the framework of the European project, we have got some funding for doing this research about the medical devices, about the certification of medical devices. So, and in Europe, this legislation is very strict for certification of medical devices. All research or software have to compile to be aligned with regulation, medical device regulation. But as we are developing a system that incorporates artificial intelligence algorithms, we have to apply also the guidelines from the European Commission regarding the trustworthiness. And so more about these guidelines can be found in a document from 2019. And along with these guidelines is also a checklist for this application of artificial intelligence in different sectors. In 2024, the Artificial Intelligence Act was promoted. It is the first ever comprehensive legal framework. We promote like that a legal framework on artificial intelligence. The rules aim to foster trustworthy AI in Europe. And in this act, and also how the systems are divided, we differentiate between systems with minimal risk, limited risk, high risk, and unacceptable risk. And medical devices and software in the service of healthcare are high risk applications. So that is important to test and validate all aspects of such system. The ethical guidelines point to three pillars of this framework for trustworthy AI. So one pillar is the lawful AI. So the artificial intelligence system should be lawful, so should be compliant with the regulation. Then we have ethical AI. And robust. So regarding the ethical dimension, we have strict recommendation or requirements, and these 7 key requirements are very important for us. So the first requirement, human agency and oversight technical. We cannot allow the system to do anything, especially in healthcare. These have to be overviewed by humans. The second requirement, robustness and safety, then privacy and data governance, transparency, traceability, diversity, non-discrimination, fairness, social environmental well-being, and accountability. So these requirements we have taken into consideration when we design the system. So I will now talk about the design of the system and how we are implementing these requirements and how we are analyzing these requirements and how we are matching these requirements with our technologies. So the Intelligent Lab project, as mentioned, is composed of 2 parts. So the study A and study B. The study A is the development of the system or testing or development of different artificial intelligence algorithms. And study B is application of this system or deployment at clinical centers in Europe, and testing and validating all features of this device that we would like to put in practice. For development of the algorithm, we are using open sources or databases that are available, as such ICU, Harvard, and Mimic. This data is integrated and used for development of the algorithms, but we have external validation also with concrete data from clinics. So Cleveland Clinic in America and also University Hospital Dresden were used for external validation. Coordinator of this system is University of Dresden. And more you can find on our links that I will show at the end of this presentation. So here we are talking about really critical systems. So these are systems for, we would like to set the mechanical ventilation of critical ill patients. These are really high critical systems. And the significance of mechanical ventilation has been especially understood after the COVID pandemic. So currently we are in study B phase. So study B phase is prospective analysis, and we are indeed deploying the system at the moment in different clinical centers. And I will talk about this process of testing and validation. So, as I said, the system has to be designed from the very beginning in a transparent way. And we are talking about ethic by design approach. And we are using a methodology for analyzing the requirements. So this methodology it's used in many domains in Europe. 62559 use case methodology. So we start with high level use cases, then we go into deeply low level use cases. And as we're talking about medical devices that have to be deployed at ICU, we are especially considering first this data integration part. So live streaming and integration with data integration systems, so pre-processing and workflow optimization. Then on the side of, so once the data is collected, so collected by the patient, from the patient, collected from the hospital information system, this data have to be with minute resolutions conveyed towards the artificial intelligence algorithm. However, here we have a pipeline, processing pipeline. And for this step of integration of artificial intelligence with the pre-processing workflow, we are using a special low-level use case. Then we have trustworthy AI, customization, explainable AI. Here we are developing the artificial intelligence algorithm. We are testing the features of the algorithm itself. It's a reinforcement learning algorithm. And then in the end, we have trustworthy AI validation on the side of medical experts. And we haven't reached that phase yet because we are still collecting the data for the prospective study. For the retrospective, we have done through the medical validation as well. So the software development process is well defined by literature. The V model diagram is used. So from concept phase, we have designed the system. Then we have a critical design phase where we have designed on a unit level. Each component have to be uniquely described. And each component have to be then first tested. So each unit have to be tested. And then we are going back to integration testing, system testing, and validation on the whole system. Each unit has its own key performance indicators. So, for example, for the first step, the data integration from the hospital, we have to evaluate the acquisition, the data harmonization, data storage, and then communication with the platform where the artificial intelligence algorithm is running. Then, for the workflow that I mentioned, it's a pre-processing workflow for the artificial intelligence algorithm. We have a set of indicators: completeness of input data, validity of input data, timeline of input data, time efficiency of the pre-processing, adaptability to pre-processing, reliability of pre-processing. So, very, very important steps, otherwise we will not have any results from the artificial intelligence algorithm. And the goal here is that the algorithm recommends us how to set the mechanical ventilator instead, or to help the medical expert to do that in critical moments, for example, during night, or in the situation was a pandemic, COVID-19. On the side of the algorithm, also a set of key performance indicator. This is the set that we defined in the very beginning of the process, and the project. Otherwise, it would be that this list is also extended. So, algorithm performance, quality analysis, error analysis, optimality, convergence, sample efficiency, cross-validation, and so on. So, when we set the whole trustworthy evaluation framework, we started that we need a database of KPIs or a repository of KPIs, and this repository we have technical KPIs and medical KPIs, as I mentioned, linked to the low-level use cases, and then all these have to be compliant with the regulation regarding the implementation of the validation. It could be manually, so the expert is checking what is wrong, or automatically, and we receive the results. Regarding the development of the system, so the system is built upon two network interlinked platforms. We have the data integration platform that is collecting the data and showing the results of the recommendation to the end users. And we have a backend. The backend is the secure platform where we have the algorithm stored, that the data is anonymized from this site. And then we have compliance with standards. For example, if these two platforms are separate, everything has to be communicated via HL7 standard. The algorithm that is on the back end, on the secure platform, is reinforcement learning algorithm. So for more clarity, the main goal of this reinforcement learning is to learn the optimal policy that maximize cumulative rewards over time. So policy refers to the strategy that the agent employs to determine its action based on the current state of the environment. So in our case, the environment is the patient. So patient with all parameters, so these are the vital parameters of the patient plus lab parameters, laboratory that is ad hoc is coming, but the vital parameters are coming with 1 minute resolution. The learning process involves exploring different actions and exploring non-successful actions to improve the policy progressively. Actions are setting up the ventilators for some parameters, vital parameters, and then rewards served as a teaching system, or teaching the required parameters, the safe ranges, and so on. In the beginning, we thought that for this concrete problem, we will need multi-agent reinforcement learning. However, with the results and with the initial and after that with the testing phase, when we pass the testing phase, we concluded that a single agent reinforcement learning framework is sufficient and also advantageous for achieving our objectives. So we started with model-free learning. So learning policy directly from the offline data set without building a model of the system dynamics. But shortly, so currently we are in the third year of the project. We already used model-based learning, built a model of the system dynamics, which is then used to learn a policy. And here we have some pros and cons. So what is plus and what is minus of the approach. I would like also to mention that this model-based was used for improving the explainability of the algorithm. So in step one, conservative Q learning was used, widely adopted by the reinforcement learning community. And in the step two, we have proposed a novel approach to provide decision-making support in mechanical ventilation through the integration of model-based reinforcement learning with explainable AI techniques. These explainable AI techniques are, they use sharp values to support explainable AI, and the experts are knowledgeable that are using the system are knowledgeable to understand what these shape values are saying to us. So which variables are more important for the predictions that are generated by the artificial data algorithm. Model-based reinforcement learning, so it's, we use conservative offline model-based optimization. And our conclusion is that it achieves superior policy performance as measured by fitted cube evaluation. Employing explainable AI techniques, we indeed are building a dual explainability layer, one for an underlying transition model and other for the policy. This not only enhances the trustworthiness and transparency of the AI in critical medical application, but also aids in understanding the complex dynamics of the ventilated patient. So now I will go through the step of validation of aspects, the integration aspects, validation of the development of the pre-processing algorithm, and so on. And as I said, this is a project that started in 2022, will end in 2027, so these results are preliminary. The medical validation will be available in 2027 for the prospective study. What is scope of validation and testing? To repeat, we are aiming for a breakthrough device, medical device. This is a class 2B medical device, and its implementation was divided, as mentioned, in different steps. So the testing is also divided in different steps. So we are testing on unit level. Some of these tests are also automated. Then we are testing on component level. For example, the pre-processing is a very complex. Once the data is collected, we cannot forward the data towards the artificial intelligence algorithm if this is not confirmed that all the values that are coming are indeed the right values, and they are in this step component testing on component level is very important in the development of the system, but also in the deployment of the system. So integration testing. So integration is when the data is collected by lab devices, by the hospital information system, using REST services that is transferred to the backend, the secure platform, and here the data is forwarded to artificial intelligence algorithm, and the data is returned to the human-machine interface. And this integration was also step by step, and the testing was step by step. And at the end, we have testing on the system level. So once again, about the design of the key performance indicator. They have to be meaningful for the specific problem. So we are addressing a few illness of patients that are on mechanical ventilation. So this key performance should also reflect the specifics of the illness. Then we have description of each KPI with formula. Also, these KPIs could be connected with additional KPIs. So this could, for example, KPIs could be connected with 2 low-level use cases, or one KPI can influence another KPI. So completeness of input data, as mentioned, was very important. Then we have the implementation. We are monitoring the execution of the workflows manually, but in principle we have some tools for this validation. And then on the side of human-machine interfaces, so here we see, for example, the human-machine interface for the medical expert. He can monitor the variables, but also he can see the recommendation, and then he can give his opinion about the performance. Otherwise, the performance of the algorithm is also compared with some automatic measures. So if something is wrong with the system, we have, for example, signaling, so different lights, so what is wrong. And then we are going in detail for this patient, what is wrong for the patient, problems with the variables, or data collections, or whatever. So on the side of robustness, robustness, safety, and security goes together. So cybersecurity measures are very important, and here we trust on the hospital systems. This artificial intelligence decision support system is implemented or is deployed behind the firewall. So whatever is appropriate for the cybersecurity measures for the hospital is appropriate for our system. Then, for regarding the privacy and data governance, this was a very important issue that was taken in from the very beginning. We differentiate between data that is not anonymized and data that is anonymized. So the data that is on the back end is anonymized, and the information about the patients has just the medical doctors who are treating or who have to use the system to treat the patient. So we have developed this role-based success for the end users. So timelines is one of the parameters that is very important for starting the analysis of the recommendations. So the recommendations will not even come if the input data is not correct, is not consistent, is not complete, it's not timeline. So that means lab data from yesterday, it's not important for the recommendation and for to recommend something to the expert, but this data have to be collected on 3 hours before the recommendation or something like that, depends on what is important. Regarding the implementation of the whole system, so we are taking care of the data provenance. So from where the data is coming, who has to see, who is allowed to see the data. So the data management, very important component, and explainability, very important, because especially in the time when the algorithms were developed, because these explainability measures or this visualization which have values was very important for the doctors to understand what is really important. Sometimes they ask themselves if we are treating well, so what we can learn from the data. So I would like now to point to the most difficult problems that we had to go through. So it's an integration in the hospital environment. So each hospital is different. So if each hospital has its own devices. So the part of the data integration was really tough. And we are currently on, we have not reached our goal yet. So we are aiming for 4 hospitals, but we have deployed the system at 3 hospitals. Communication between the 2 platforms, yes, it is very important, because we do not allow to come out with some recommendations is if the data is not appropriate, it is coming. Then we have, this is the business logic in the pre-processing pipeline. Compliance with standards, very important. Why? Because in order to put the device in hospital, we have to go through some checks for ethical committees and sponsor committees to get the right yes on the side of the legislation, but also on the technical side. So the documentation for testing is quite big. And the standards that have to be used should be in regards to the interoperability with the environment, so should be on a very high level. So we are talking about standards that are already in place in hospitals, so we have to adopt to that standards. We cannot change so much, we should adopt that standard. And then export the data, whatever we're doing in that format that is already in place. And I would like to mention that this is not my work, it's a work of the whole consortium. So here we can see moments how we are working. So we have once a year a general assembly where we are talking, we are discussing the results. So these results have to be validated, and the medical doctors, although they have their regular meetings, this general assembly once a year is very important when we all together, technical team and medical doctors, are discussing the results. The dataset preparation, either for the retrospective study or the prospective study, took longer than planned. So it's a process. When we talk about the artificial intelligence algorithm, we don't think that we should indeed, and the time that we have to reserve, indeed, we have to think about this step. Findings from our research on using reinforcement learning is that the training policies improve the performance versus the clinical actions. So we achieved for the data that we have prepared, carefully prepared, they outperform the clinical actions by this evaluation method that we have selected, especially on safety related. But this result is coming from the retrospective study, so it's coming from the data sets that were used for training the algorithm. We don't know what will be the evaluation in 1.5 years. In 2027, after we go through the clinical study, so the clinical study already started but it will last for 1 year. So what will be the results? So this is really a preliminary results of the work. So here are some links where you can find more about us. And it's a consortium of almost 20 partners, and this project, I would like to acknowledge, it's a project funded by the European Union. So I would like to thank you for your attention. I would like to also invite, if there are any questions, you can send me on mail. And if you see some potentials for collaboration, just let us know. So this is the presentation that I have prepared for today.
Thank you very much, Madam, for your excellent speech. I would like to call our convener of Sswc 2025, Dr. Shoma Shah, as as we are not having you offline, so we have to present the token of honor via online. So, Dr. Shobhabrata Shaha, convener of Sswc 2025 is here to do that.
Thank you, ma'am. This is a great opportunity for all of us to listen from you that you are so busy with all your activities. But we are really feeling privileged that, ma'am, next year we can expect if you come to India and visit our organization and attend this SSWC, we will go on. I will be communicating with you, ma'am, in the over mail. And okay, ma'am, this is a.
Thank you. Thank you for the invitation. As you invited me this year as well, but the situation is like this, so it was difficult for me to travel.
Ma'am, this is a small memento we are sharing in the digital platform. Ma'am, kindly accept and we are sharing to you through your mail.
Thank you.
Thank you. Thank you, ma'am, once again. Thank you. Thank you, ma'am. Bye. Bye.
We are really honored to have with us Professor Nabarun Bhattacharya, Director of the School of Information Science and Technology at MACOUT. I would like to sir to come up on the dais. Now I would like to request Dr. Shobhabrata Shaha, Head of the Information Technology Department and Convener of Sswc 2025, to felicitate Professor Nabarun Bhattacharya. Sir, please. Professor Nabarun Bhattacharya from MACOUT is a former senior director and center head of CIDAC Kolkata, with notable work in agri-electronics and sensor technologies. With utmost respect, I invite him to deliver his keynote address. Sir, please.
So, good afternoon. Lunch is approaching. So, I am standing between you and lunch. So, please bear with me. And you have got wonderful talks on chess, also some data flow models and the previous speakers. So, that is my destiny. I am always preceded by great speakers. So, I just try to speak something else which may interest you, may not be interesting to you. The topic I want to delve on in this half an hour talk is multi-sensor system. That's one point. That is the highlight of my topic is multi-sensor system. And not only that, it doesn't end there, then neuromorphic edge computing with multi-sensor, and then some electronic perception technologies. We have perceptions. We have got 5 senses. That is touch, smell, vision, hearing, and smell. So, these how to implement electronic perception systems using multi-sensor systems and neuromorphic computing, and of course, there will be smarter solutions, not smart. There will be smarter solutions, and I'll quickly, there are a lot of slides, I'll skip a number of them as I'm going to go, and all these things are maybe the future of various state-of-the-art applications in the field of agriculture, environment, healthcare, and so on and so forth. So, sensors, all sensors. We are all IT people, and they can be based on functions, they can be sensing principle, they can be based on the type of output it delivers, or based on the power source. Some sensors may be passive sensors, some sensors may be active sensors. So these are the sensor taxonomy by function, starting from temperature up to biosensors. Sensors can be biological also, your glucose measure. It's a biological sensor because the receptor is biological receptor and it accepts a particular biological molecule. So there may be by function a number of sensors. We know. Then sensors by sensing principle. We all have a little bit idea about electronic principles of working. They may be a resistive sensor. So some parameters, physical parameters, when the sensor is exposed to, the resistance changes. So that they are the resistive properties, transduction principles. There may be magnetic, there may be piezoelectric, and so on and so forth, capacitive, etc. Then there may be by output type. Some sensors output may be different types of outputs can be there. Sensor taxonomy by power source, active and passive sensors. Some sensors power themselves, some sensors get power from outside. So this is the types of sensors, because I told you we want to implement electronic perception system through multiple sensors. So I gave you an overview of sensors. Then other notable types, there are latest some sensors are there. Latest development in the sensor field. They start with smart dust, quantum sensors, the principle of superposition and entanglement. It is parallelly being developed with the quantum computing, quantum communication, quantum simulations. So this is also one area. And all sensors are now converted to IoT devices because sensors are connected. Sensors are connected. So no sensors, standalone sensors are there these days for advanced applications. So sensors are, so there are a number of this kind of smart sensors that is making a lot of noise in the field of technology. So these are the few of the diagrams what I have told last 7-8 minutes. And application of sensors are everywhere, this need not be repeated. We have got a smartwatch, there are a lot of sensors there. So we have got your mobile phones, there are sensors. In your home, if you are falling sick, you have a thermometer sensor. These days digital thermometers are there. So sensors are there in automotives. In any car, there are any number of sensors these days. Smart homes, healthcare, and industrial automation. Some machine is running, what is the temperature of that process or product, what is the rotation speed, what is the conveyor speed, what is the ambient humidity, etc. Those things are measured in an industrial ecosystem. So these are the applications. There are other things, environment, robotics. When a robot is moving, it is guided by sensors only. Camera is a sensor. LiDAR is a sensor. There are GPS monitoring for the position. So they are all sensors. Then consumer electronics, agriculture. So these are the applications. And these are the various application photographs that I have tried to give. So what I have told, that there are a number of sensors, very simple. And those sensors are finding applications everywhere in today's day-to-day life. Now, when I am using a sensor for any application, suppose in this room, I want to monitor what is the relative humidity or what is the temperature. What I use a single sensor, temperature sensor or RH sensor. So that sensor gives me specific outputs and I'm happy with that solution. So single sensor systems are very simple systems. They are simple, they are based on the requirements, exact requirement they cater. They are cost effective, reliable. But when a complex situation is there, suppose I have to measure the concentration of a gas from the air. Now air has got a number of gases and I have got only suppose H2S sensor, hydrogen sulfide sensor I have. But what will happen? That other gases will also disturb that sensor and these sensors may not be as sensitive to catch the target gas. These are the demerits. So limited by the sensitivity and selectivity, then limited by accuracy, limited range and complicated fabrication method. Because every application you have to make a single sensor system, every application there should be a sensor. And that makes the fabrication very difficult. So this lays down the platform for a multi-sensor system thing. So this is single system, single sensors. Maybe vision, olfaction, digital camera, metal oxide semiconductors. They go to interface, there is a computer data acquisition, then you do analysis. So this is a normal single sensor system issue. But multi-sensor system and sensor fusion, that can solve a number of problems where not only single sensor system used to be facing a lot of challenges, but also multi-sensor system can solve very efficiently the problem of a single sensor system also. Like by the name, multi-sensor means a number of sensors together. So whatever is sensed, that is sensed, and the pattern is analyzed. Output pattern is analyzed to really correlate with your real world annotations. And this is what multi-sensor system, actually sensor fusion is the core process within multi-sensor system. You have to take all types of sensor data together and then extract the intrinsic pattern within that data output to really do any clustering, do any classification, do any identification, do any correlation, whatever is the task that we want to address. Now, what happens if there are number of sensors? Every sensor, let there will be cross-sensitive. You need not bother about fabricating highly selective or highly sensitive sensor. You can have whatever is the selectivity, whatever is the sensitivity, a multiple sensor sense the whole pattern. And that pattern will be repetitive and reproducible for a target compound that you are going to sense or a target atmosphere you are going to sense. So this is what is the beauty of multi-sensor, where accuracy may be increased, reliability enhanced, improved robustness, provide more complete picture and leverage cross-sensitivity as being another. See, otherwise cross-sensitivity in a single sensor system is a problem. But here, cross-sensitivity only is the enabler. So this is the multi-sensor system where you can see I have seen a camera, a sensor, motion or temperature all together. You take the output as a multiple dimension data and you analyze that. So then what is a sensor array? We use this sensor array term a number of times in sensor applications and data applications. Actually, sensor array is a subset of a multi-sensor system where in a single spatial distribution, you have number of the sensors of the same type. Like there may be camera, there may be a temperature, and there may be a metal oxide semiconductor array, MOS array. So same type of sensors in multiple numbers that can capture the spatial distribution of an event or of a targeted ecosystem. So sensor array is a specific type of multi-sensor system where multiple sensors of the same type are arranged in a grid or other defined pattern. This allows for spatial mapping or analysis of measured parameters. So this is multi-sensor system, various types of sensor, and sensor array can be part of a multi-sensor system but consist of the same kind of sensors. Why I am talking all these things is because this multi-sensor system can be backbone of the electronic perception systems of the world. Now, I'll tell you one more small concept of neuromorphic computing. Now, we all know that normal computing has reached very high capability stage. That is, high performance computing is possible today. Its services are offered to cloud. When you get any cloud service, actually a big data center is running over here with high performance computing, virtual machines. Now, the issue is that in a data center, suppose this ChatGPT is running, multiple huge data center, and the kind of power that is consumed there is to the tune of gigawatt and even better, even higher. The kind of cooling they have to do to really cool down the computers is highly power hungry. And there are debates all across that how to balance this power demand for machine learning based applications like the AI applications you are having today, Gemini, Grok, DeepSeek, ChatGPT, and whatnot. Now, these can be countered only by neuromorphic computing. You know, our brain is highly parallel, and our brain processes huge amount of data. It handles huge amount of memory, but the power consumption is very less, or it doesn't get heated up. Because our brain architecture is neuromorphic in nature, where every neuron works as a processor and does partial processing. When the information passes through the neural pathway to our brain, in the brain, it's not the central processing unit is on. Every neuron is a processor, and every synapses in the memory. That is the connection between neurons. And this architecture reduces the power demand by not 10x time, 100x time, maybe 1000x time power demand may come down with neuromorphics. And if neuromorphic use at the edge. And this has got specially this neuromorphics, why it is special? Suppose I am looking at somebody. My brain will not keep on capturing data like if you have a CCTV camera, every second it will capture data and store in your memory. But human beings, once captured somebody's face, will be there. If there is a movement only, then only second set of data, second stream of data will be captured. And that is called spiking. neural network with spikes, with some trigger. I capture only that data. Useless data are not captured. And in normal computing architecture or Neumann architecture, what happens? If you want to make 2 plus 2 is equal to 4, then first 2 will be kept in the memory, then from memory it will be going to processor, then once again 2 plus 2 will be there. Now if you want to make 2 into 50, so 50 times 2 will be that operation will be between memory and processor, memory and processor. So that is the reason of power going high. Whereas neuromorphics doesn't do that. It does processing at the edge with spikes, with triggers, so that power consumption is less and highly parallel. They are not serial. So time taken also is less. So this is one more topic scientists all across the world are looking at very seriously. So this is what I told you how neuromorphic computing works. It's just like our brain through neurons, inspiration from neuroscience, and highly parallel and distributed. Highly parallel and distributed. So potential applications, anything and everything you think today based on AI, based on machine learning, they can be done through neuromorphic intervention. Now, von Neumann versus neuromorphic, I told you that for normal computer architecture, memory and processing separate, and they are keeping on exchanging data through the bus, data bus. So that is the problem. And neuromorphic addresses this, just like our brain has never gone in the von Neumann way. They have a natural way for less power hungry processing systems. This is spiking neural network. Only when you move, my vision only will capture your movement, not when you are still. But in a normal IT computing infrastructure, we can keep on capturing many unnecessary data. That is not done in spiking neural network. So neuromorphic compute is brain-inspired, parallel, and low power. Please keep this in mind. And this is the coming up paradigm in the computing domain. So neuromorphic chips, and there are some chips and models available now. I have given some names: Intel Loihi, then IBM TrueNot, Brain chip. Brain chip is one Australian company. They have come out with Akira chips. Then spiking neural network architecture. This is by University of Manchester. There's a project on it. Then BrainScale developed this University of Heidelberg. They are doing a project on this neuromorphics. And Synsense, this is a commercial chip which offers this neuromorphic chip. So there are intense research ongoing all over the globe with neuromorphics. So need for sensors and edge computing, because we are going to, I'll take just 5 more minutes, and we are going to the electronic perception systems, where computing in the edge is very essential to really make the system smart. That is the theme of this conference. So electronic perception systems are, we have developed electronic nose, electronic tongue, and electronic vision systems for various applications. And these systems can be powered by multi-sensor systems and neuromorphic architecture. So electronic nose means when there is a smell, that smell can be detected. Smell is caused by volatile organic compounds. And that volatile organic compound mix, if can be routed to a sensor array or a multi-sensor system, there will be definite patterns coming out, and we could develop Electronic vision also. Electronic vision is nothing but computer vision, which you can capture the image, color, texture, appearance of any object and classify or cluster. And electronic nose and vision system, this is the system that we have developed at CDAC for tea, black tea. You know, tea testers are there. They sift a couple of sips and based on their appraisal, the price of tea is decided. And that is highly subjective and human dependent. So we replaced this with electronic nose and vision system where sensor arrays capture the aroma and vision captures the visual traits of black tea. That's also very important, the granular size, whether tea color is coppery brown or black. And those things decide the price. So this is the system. The electronic tongue also. See, we have got 5 tests, and that can be mimicked by sensors. And electronic tongue we have developed using electrochemical sensors, and they can find out the strength, bitterness, astringency in a tea taste, or maybe wine taste, or maybe any other food or beverages. So this is the electronic tongue system that has been developed and commercialized when we work in CDAC. And these are many other sensor-based systems for rice, for cardamom, for soil quality, for a number of health applications, for pesticide residue in vegetables or agricultural produces. We develop different kind of sensor, and all these systems are developed using multiple sensors and sensor arrays, collecting the pattern and recognizing the pattern using AI engines. So now, this, if you want to go for an affordable, intelligent, neuromorphic electronic perception system, it's possible because you have to develop a generic sensor array framework for any application, multi-sensor framework. You need not have selective and sensitive sensors. And then you can integrate with that sensor array to various applications. You deploy edge computing, you incorporate neuromorphics, and the entire system, maybe a generic framework, only you change the software. So that you get an electronic perception system in reality, and real work is happening all across the globe in this field. So these are the various, maybe these applications. Essential work elements, this is fabrication, then edge IoT devices, experimentation, and we have to go, we have started work in this field. So these are the 4 stages. We are planning to really take the project to. So final electronic perception system will be a small system with few sensor heads, and you take it for any health application, agricultural application, environmental applications. You can have the results. And my last word, that days are not far off, because now we are mostly on virtual world. We are seeing our mobile. Suppose you see on a mobile a very good recipe being cooked, but you don't have the smell, you don't have the flavor, you don't have the taste, you can't touch. That may be possible if such systems are in place where you can really have the look, feel, touch, and all kinds of senses and perception implemented in these cyber physical systems. Physical system and cyber system can be really converged and integrated together. Thank you very much for your patience.
Thank you very much, sir. I am requesting to stay here for a while, to stay on the desk, and I am requesting Dr. Subarna Dasgupta, Joint Convener of SSWC 2025 to present token of honor to sir.
ও তোমরা
Thank you, sir. I am requesting all the authors from technical session 2A and 2B to go to the respective rooms, that is main building room number 403 and 404. Only the authors from technical session 2A and 2B, which is from 1 p.m., go to the respective rooms at main building room number 403 and 404.